This is a virtual helicopter taking off. To control and take off, you need to increase the collective pitch angle of the main rotor. But due to the reaction torque from the main rotor, the helicopter frame would rotate to the opposite direction. To compensate this behavior, you need to control the tail rotor to cancel out the reaction torque. However, doing so with this interface is not so straightforward, because this interface is designed as a raw actuator inputs. Without an autopilot's help, this is quite convoluted control interface for a human to manage this. If you think you can do this, like manually control this by yourself, please comment down below so I can learn from you. Otherwise, I'll go over the control algorithms to manage the helicopter's flight in Python using ROS2. Alright guys, this is Elia. Welcome back to my channel. Today I'm going to talk about helicopter simulation and control using Python and ROS2. So to begin with, just navigate to this URL. I'll put this down in the description section. And then click this guy, helicopter height control over helicopter, whatever that is. And then it's going to load. And this is the helicopter on the web browser simulation. And just in case if you never heard about this virtual robots, my website, this simulation works like this. That's a specific virtual robot just like a helicopter in the web browser, and then this can communicate with ROS bridge like this. And then bridge will just parse all the data and then will broadcast into ROS standard data protocol that each of the nodes like a robot controller can subscribe the state from this simulation, and then it will publish the command input back to the simulation. And then that's how you control this helicopter. And then what is this bridge? It's just like this. So if I go back here, that's my Git repo. I'll go over this a little later. But as you can see, ROS VR, Virtual Robot Bridge, is just one of the packages in the ROS system. And then you'll just build it, and then they're ready to go. So you don't really have to worry about all this infrastructure, how to connect a node to another node and so on. It's done there. So you can just focus on this specific control algorithm in Python. If this is your first time handling the helicopter control and how it flies, let me briefly go over that really quick. Alright, let's talk about the lift equation first. So let's assume this situation, the airplane is flying forward, and then the air is just static there. There's no jet stream, no turbulence, no nothing, as the air is the wing will encounter this airflow, the relative velocity, and that's called free stream velocity, V infinity. And then the lift equation is like 1/2 times rho is the air density, and then V free stream square, and then times S is for the area of the wing, and then CL is the coefficient. And that's it, just plug in the number and you will have the value. Point here is that lift is just proportional to the square of the free stream. Now, lift of the helicopter is basically the same. Only difference is that airplane needs to go forward to see the relative velocity, the free stream velocity. A helicopter doesn't have to do that because the blade is rotating, and then the relative velocity of the air is like this. It's just blowing all direction because it's rotating really fast. And then same exact lift equation. Now here CL is the lift coefficient again, and it's a function of alpha. Alpha is angle of attack. Angle of attack is just angle between your chord line of the wing and then free stream velocity, and that's angle of attack alpha. And then CL, the lift coefficient, is just a function of alpha, like this graph. Lift coefficient here on the y-axis, and then x-axis is AOA, angle of attack. And then as this alpha increases, the CL increases as well. However, at a certain point, I don't know, 17-ish degree, it will start to go down, and then we'll just like no more lift coefficient anymore, which means the airplane will be just free falling. Now let's look at this helicopter free body diagram. X-axis towards the front of the helicopter, and y-axis towards the right side of the helicopter, and then z-axis towards down. And that's just the aerospace engineering convention. And then in this free body diagram, helicopter is rotating counterclockwise, and then pitch up a little bit, say, I don't know, 5 degrees and so on, so that it doesn't stall, but it can generate a certain amount of lift. And then here, the force due to the main rotor is depicted as F main X, Y, and Z for X, Y, Z axis. And then total force for X, Y, Z axis is depicted like this. Then that's the F tail, because tail rotor is also rotating like this. Why do we have a tail rotor, by the way? as this main rotor rotates counterclockwise, and then reaction torque, this main body of the helicopter will rotate clockwise direction. And then we need to compensate this clockwise torque, and then we want to generate the force that direction by blowing the air like this. And then we can compensate this reaction torque, and that's why we have tail rotor. And now we're talking about this helicopter is just hovering in the middle of air, and then using this good old-fashioned engineering class trick, everything goes to zero. And at the end of the day, we'll be left with just two equations like this. So from the simulation, if we want to just lift this helicopter, we can just increase the pitch angle of the main rotor, the collective pitch, and then it will increase the force to upward direction, and then torque will be generated as well as we increase the main rotor. And then to compensate this reaction torque, we want to pitch up the collective angle of this rotor as well. And let's just try this. Hey guys, this is Elliot. If you find this video helpful, please like, share, subscribe for more tutorials and tips on robotics engineering. To begin with, let's just navigate to this URL and then click this flight control helicopter. Now it's just going to load this. Now we have loaded this helicopter control simulation. And then to simply turn on this collective pitch angle, you can just turn on the manual and then increase the collective pitch angle for this main rotor. Then it will generate the lift and helicopter will take off. However, there's a tail rotor doing nothing there, although it's rotating, but there's zero collective pitch angle for the tail rotor, so you just need to increase this to compensate the reaction torque. Then it stops, and then it will come back to there. Okay, that just crashed it. Let me reset that. And then this again, and then increase the tail rotor pitch angle together. Then I can control the heading of the helicopter like this. But now I need to control the altitude of the helicopter, but at the same time, I need to control the pitch angle of the tail. Okay. All right, that's not easy. We need to do this in Python. Stop it, turn off the manual. Now to start with the ROS, I have README file here, and then the assumption here is you have access to Ubuntu system, and then I have Docker installed on this Ubuntu 22 on my WSL. And then if it is first time using Docker or WSL, I'll put another video about Docker. Please check out the link over there. Let's start from here. You have a Ubuntu system and then create a folder like robots workspace, and then create a file, Docker, and then compose, and then YAML. And then next thing is just copy paste this, and then the terminal at this location, just type Docker, compose, and then HD. And then your Docker container is running in this Ubuntu system. Attach VS Code here, and we are ready. Now I open up a file explorer here. There's robot workspace and then source folder there. Now what we're going to do here is that first we're going to install PIP packages for these virtual robots. Just turn on the terminal, copy paste, and install this. Then next thing is to copy all these ROS packages that is built in already. Open integrate terminal, copy paste all these git clone commands. Then it's ready to go. It's already there. I'm going to do is cd robot ws. Increase this a little bit. Okay. So under this path, just type, and then actually, let's not type it because I'm not good at typing it. And then paste this. That's the build command in ROS2. Then it's just going to build all these packages. And then the next thing is to run this bridge, and then to be able to connect with this simulation. Before we do that, let's just source, install, set up the bash, and then run this, and then the bridge is running. And then if I go back to the simulation, click connect, now there is a green light. It means it's connected with this bridge. The next thing is that we want to run this script. But before running that, let's just go over the code a little bit about this helicopter controller in Python. So if I just open up the main file like this, it's just a boilerplate code for ROS node. What it does is just define the system ID of this helicopter because the simulation comes with the specific system IDs, like something like this. So that's a system ID that we want to control. And then define the subscriber and publisher. Subscriber is for subscribing the state messages from the web browser, and then publishing the command so that we can let this helicopter in the simulation know about what kind of commands is coming in real time. So that's what the publisher is for. And then what we need to implement is this heli controller. And then the rest of them is just how we want to pack the data so that the command data can be published to the web browser. Anyway, let's look at this update part first, command helicopter control. So let's open up this heli controller, and then there are a bunch of codes, but these are just simple PID controllers and they are being repeated. And then why they are being repeated? Because we want to control specific axes like X, Y, Z, and we want to control the rate of axis, and then we also want to change the attitude of each axis and position, velocity, and so on. So that's why there are a bunch of controllers here. And then in this update function is the actual function that is being called on this publisher. Then we are controlling the altitude here. The set point of the z-axis altitude is -20, and that's because the z-axis of the helicopter is towards downward, and then we want to go up. It means -20, and then what it does is calculating the error. Set point minus my current position, which is 0. And then the error at that time should be -20. And then based on this error, this PID controller will calculate the set point of the velocity, the climb rate of the helicopter, or sink rate of the helicopter if it needs to come down. And then that's the velocity set point. And then again, the velocity set point is fed to another error calculator for the velocity. Then it will compare with its own current velocity of the helicopter, and then it will adjust the velocity of the helicopter based on its position controller. And then finally, this PID controller will output the collective pitch angle of the main rotor. Now I'm just clipping it between 0 and 7 because we don't want to go outside the range of these numbers for the pitch angle of the blade. And then all the way down, we are actually, by the way, we're going to talk about all these commands in the later videos. It's about the cyclic control of the helicopter. So let's skip this for now. And then what we want to turn on is just this part, body Z rate, and then body attitude control. And that's for controlling the tail rotor's pitch angle, because there's a reaction torque from the main rotor, because we are only controlling the main rotor up here. Now we need to compensate the torque from the main rotor by adjusting the tail rotor's pitch angle. So our set point of the heading of the entire helicopter body is 0, which is just the default 0. Then we calculate, same thing again, just using the same type of PID controller. We can adjust the turn rate of the helicopter for z-axis, and then using this rate set point, and then compare that with the current z-axis rate of the helicopter, and then just calculating the collective pitch angle of the tail rotor. And then it's just returning all these values. For now, these two are just 0. And then let's just run this. Let me turn on that now. And the bridge is running. I'm going to source, install, set up the bash so that the terminal can know all the environment variable of this code. And then to run this, just run this code. This command to run the helicopter. So just type it like that, and then since it's connected already, the helicopter is going up all the way up to -20 meters. And then the tail rotor is doing its best to control the pitch angle of this. Actually, Python is doing its best to control the pitch angle of the tail rotor, but anyway, it crashes because this helicopter is moving to the right side of the helicopter. Do you have any guess why? If so, please comment down below. Anyway, that's the end of this video. We have controlled the altitude of the helicopter, and then at the same time, we're controlling the heading of the helicopter as well. However, in the next video, as you can see, we need to fix this part because we don't want to crash. I'm going to talk about cyclic pitch control, and I'll see you in the next video.